Doesn't work? Yeah? All right. My name is Elad Hazan, and this is a joint open problem, I guess, with Livni. And it's about unsupervised learning. So this came out of teaching, actually. So when teaching learning theory, doesn't work? Let's see. How's this? All right. Good thing I didn't say anything so far. So when you teach learning, when you teach supervised learning, we have a lot of theory to teach the students, and we can put everything pretty much on the same footing and compare models and compare results and talk about generalization and a lot of interesting things. But when we teach unsupervised learning, every kind of component has its own theory, and they're not so well connected. And one of the most important things we do have in supervised learning is we can come up with efficient algorithms that step outside of the class. So what we call learning by convex relaxation or improper learning. So Dylan Foster and his co-authors talked about it even in this talks when they show how to learn logistic regression, right? But not through the model. If you just try to using logistic regression, there was a previous lower bound that showed it cannot be done, and they show something better by stepping a little bit outside of the class. And we don't have something, and there were more papers, even in this course, that use this technique. But we don't have this technique for unsupervised learning. And that's why it's well motivated, in my opinion, to think of unsupervised learning as compression reconstruction, so loss minimization for reconstruction error. And then you can use all sorts of wonderful techniques that we know from convex optimization. So let me give you an example. A mixture of Gaussians, which we all know. So we have data coming from a mixture of normal distributions, and we're trying to find these normal distributions, the mean of them, and the standard deviation maybe, or covariance that generated the data. And you can write an objective, which sort of corresponds to max likelihood, and it is finding a set of k-centers that you minimize the expected distance squared to the center of the Gaussian, the closest Gaussian, right? Philip says no, but it's close to it. This is close to the max likelihood. For a spherical, it's true that it's a bit cheating. I mean, I only have 5 minutes, otherwise I could be more exact. So this is close to max likelihood, and in my opinion, it's well motivated regardless. So you're trying to minimize reconstruction error over your model. And if that's what you're trying to do, this is a hard problem. So if the way it's written here, it's not exactly MOG, but it's worst case, this is NP hard. So this motivates the use of convex relaxation. Can you do something, nevertheless, to solve this problem? And turns out you can, because once you have a loss, right, you can talk about stepping outside the model and trying to do something else. Even a worst case scenario. So for example, you can do the following. So you can write your objective, and you can do a relaxation. So instead of finding a single point, a single mean, that is the closest, you can find maybe a mixture with even negative coefficients whose Euclidean norm is 1. And then you do some massaging of the objective. It turns out this is the same as finding a matrix, a rank K matrix, so that the projection of the data onto the matrix is as large as possible compared to the original data. And if you recognize this, this turns out to be PCA, KPCA. Okay, so in other words, so I started with trying to find center of Gaussians. I ended up with KPCA, which we know is efficient, right? We can also have PCA, and in PCA try to find a set of directions that represent the data in the best possible way. And now I can think of it in terms of compression. What I did is I compressed every point to k numbers, right? Those projections onto the k vectors that I found. And in terms of compression, I have k log 1 over epsilon bits to represent my data, which are provably as good as if I were to represent my data by k Gaussians, mapping each point to the center of a Gaussian. Okay, so if I were to do the mixture of Gaussians, then I would have a more succinct representation, right? Because I only took to tell each data point which center it corresponds to. So I have k centers, I only log k bits for this, as opposed to k numbers. Okay, so this is less efficient representation. It's probably as good in terms of the mean square error, but it's less efficient. So it cost us. We moved from log k bits to k, and furthermore, it's even worse. We're stuck at d. So PCA is only defined up to dimension d, right? We cannot do it more than d. And mixture of Gaussians, you can have the over complete case. You can have more Gaussians than dimension. And this approach will not scale for more Gaussians than dimension. So the question is, and here, Seb, you can get another $100 next year. So find me a compression scheme that compresses mixture of Gaussians better than PCA. So I want polylog k bits instead of k, and epsilon additive error compared to the best mixture of Gaussians. And another $100 if you can do it for the general non-spherical Gaussians, which I think is also interesting, and there are some directions too. Or by the way, these amounts, I will also give them to you if you prove it's impossible. So either come up with an algorithm or prove it's impossible. And I think there are a bunch of other, so in general, I think that this is a useful way to think about other unsupervised learning problems. And if you want, talk to me at the break or some other time. So thank you.
Short question while you set up.